everyone. So thank you for joining us today, and let's start today's session. So yeah, without a doubt, blockchain technology has grown in popularity in recent years, and blockchain technology produces, for example, a structure of data with inherent security qualities. So that security is based on principles of cryptography, decentralization, and consensus, which ensures the trust in the transaction happening underlying. But however, many blockchain security issues have arisen due to the faulty technology implementation. So therefore, our today's session is focused on understanding security challenges in blockchain. Swati is a cybersecurity enthusiast trying to explore multiple domains in security, learning and keeping herself updated with latest trends and techniques. She also serves as an active volunteer for CRAC Learning and NULL community to help building talent in cybersecurity research and awareness. So thank you, Swati, for joining us today. The stage is yours.
Thank you, Manjiri, for handing over to me. So yeah, hi everyone. Good morning, or good evening, and good afternoon, since we are based in different time zones. I'll start sharing my screen quickly. One sec.
Yeah, go ahead.
Are you able to see my screen?
Yes.
Okay. So welcome to our session today. Just to give a high overall idea what we'll be discussing in today's session. We'll be considering some of the basic overview of blockchain itself before we jump to the security aspect, so that we build the right set of fundamentals before we understand some basic challenges in security. And this can be considered as a blockchain security 101 session, where any questions you have, please post it in the QA, and I'll try to take a break in between or simultaneously answer those with the help of the panelists here. So let's begin with understanding the blockchain concept itself. So what is a blockchain? In simple terms, we can say it is a distributed database or a ledger that stores transaction or any events based on different application contexts. So if any application is leveraging blockchain technology, there can be different set of transactions or events happening as part of that application. So depending on the application context, there can be different sets of data that can be stored in this distributed database. It is distributed across multiple nodes in the computer network, and it varies from a typical database in a manner where the data stored in blocks is a set of data, can have different nature of data that can be stored. It can be transaction related data or any events in case of other application. It has certain capacity which is defined for that particular block, and also these blocks are linked via strong cryptographic algorithms. In this case, we have the hashing algorithm, which preserves the integrity of the transaction as well as the entire blockchain. So the most popular use of blockchain in the current technologies is for transaction ledger. However, there are multiple other applications which are coming up with new products using the blockchain technology. We'll discuss those also in the upcoming slide. The most popular way of using blockchain is decentralized way, so that there is no single entity or a third party government bank company which is having that control. Rather, it is a transparent network where any user can participate, and that transparency also adds to the security value. Now we have the blockchain copies maintained over the network. So with that set, it not only ensures the availability of the blockchain, but it also offers that transparency and check on the discrepancy in data in case there is any modification in the one of the copies of the blockchain which is not consistent with the entire network. So that way, it establishes a trust. In addition to that, the decentralized blockchains are immutable. that is the transaction which is recorded in any blocks, any of the blocks. It cannot be reversed. So this ensures that anyone can audit the public blockchain and see the data. It won't be tampered with, and the integrity is maintained end to end. So for understanding the blockchain completely, there are multiple other components, but we'll try to focus on some of the important ones we need to understand the security challenges. So here you see there's a block structure which is being defined. So in case of blockchain, the last node which is there in the chain is called the block itself, which is the ending block. And whenever there is a new transaction that is coming up, it will be populated in a particular block, which will be appended to the end of this existing chain. The new blocks will be appended to the chain by using certain mining and consensus algorithm, which we will discuss in the upcoming slide. But this is how the simple structure would look like. There's a last block, as you see on the left-hand side. And then the new blocks comes into place, which will be pointing to the last block as the previous pointer. So you can see there is a hash of the last block being stored in the block header. So that ensures that there is a unique identifier which can determine which is the previous block for this particular new block being added. Then we have the Merkle tree root hash also in the block header. So you can imagine picturize the transaction hashes being stored in the form of a tree, let's say a binary tree. And the parent hash is constructed based on the hashes of these individual transactions which are listed in the block. So the Merkle root hash will determine that any mismatches in the transactions which are listed in the block will be caught in case there is a difference in the calculation of parent hash in the form of Merkle root hash. So that hash is stored here, and it ensures the integrity of entire block and individual transactions. Then there is a nonce attribute, which we'll again discuss in further slide, but it is a parameter which, based on which it is confirmed that there has been some work done on top of this block, which confirms that this transaction is legitimate, and it can be used to verify the block by any member in the blockchain network. Apart from that, there are other metadata which could be stored. For example, the version, like the software or the protocol that has been used, then the timestamp of that block when it was created, and there is also a difficulty target. So there is a certain mathematical challenge which is being given to the miner. So the parameter is defined based on these difficulty target value. We'll also come to that part in the upcoming slides. So here we talk about the mining and consensus process in slightly more detail. We won't be digging deeper into it, but let's just get a quick idea about it. So mining is a process by which new blocks are confirmed, and also they result in incentives for the miner who has confirmed that block. So the incentives are offered in the form of awards, any coins which are minted for that particular miner. Whenever there is a new block coming into the network, the miners are listening to the updates, and based on different awards awarded, assigned to a particular block, they will try to pick up any random block, or they will prefer one block over the other in order to win a larger award as part of the mining. So they will pick up any block and verify the transactions listed as part of the block by working on a mathematical challenge given to them by the blockchain network. So there is a target hash which is given to them, and the miner has to come up with a hash which is closest or equal to the target hash by using multiple cryptographic algorithms to calculate a hash and determine a random variable which when hashed with the block's data will give us the target hash or something closest to the target hash. So any miner who is able to determine this random value in the least amount of time will be awarded. And as per the consensus algorithm, majority of the network will vote for the value they have given, and they will agree on confirming that block. So once the block is confirmed, it will be appended to the blockchain. And the parent blockchain will now sync with other chains in the network. So that is a quick idea about mining process and consensus itself. And when we are talking about consensus algorithm, there can be different algorithms. For example, proof of work is one algorithm where the miner has to do certain amount of work. For example, in case of Bitcoin, there is around 10 minutes taken per block to mine. So with the help of that, it can confirm that they have spent some amount of resources to determine that random variable. And based on that, they can confirm the transaction data. There is other consensus algorithm, also proof of stake. It doesn't utilize as much as energy as needed in case of proof of work. So it is slightly more preferred over the proof of work algorithm. And you will see the latest blockchain technologies mostly using proof of stake or other algorithms where there is lesser wastage of resources. The next important piece we want to talk about is smart contract. So just like how we have contracts in physical world, like real world scenarios, there are paper-based contracts where two parties will agree on a certain set of protocols, and once they are agreeing on that set of protocol, they will build a trust, establish a trust between them in order to do any action. So similar way, smart contract in case of blockchain technology is a digitized version, you can say, and it is programmable, and it will define a set of conditions which need to be met before an action can be executed. So it is an event condition action stateful program which is stored on the blockchain network itself, and it establishes trust between two or more parties who are reluctant to trust each other electronically in this decentralized blockchain network. So let's take just a quick overview here. On the right hand side, you will see we have the overall picture of the blockchain network. The right bottom has the blockchain itself. We have the miners in the network on the top right side, and there are users who are interacting with the network for different use cases. So the use case could be, let's say, withdraw money, deposit money, or release any funds. So the users are participating in this open network, and contracts are also stored in memory. The smart contracts here, you can see they are stored in memory with certain storage requirement which they have, that is also present in the network. So the miners, what they will do, whenever there is a transaction satisfying the smart contract conditions, they will consider that block and pick it up for mining before pushing it to the blockchain. So let's just take a simple flow example here. So let's consider that we have a current state where there are multiple coins and wallet addresses which are being listed. On the left hand side, you see that this is the current state, and there's a new transaction that comes into picture. Now, the smart contract is a self-executable piece of code which will trigger whenever there is a new action which needs to be performed. So here, as per the smart contract, any new transaction which comes into the network will need to follow certain set of conditions in order to be called as a correct transition and have a new state defined. So we are just taking a simple example, but here the conditions listed can vary in case of different application. So in this case, if we have, let's say, a new transaction comes up and it says spending certain amount of coins, and each transaction has a signature defined corresponding to them. So what a logic will check is whether the current state has that coin, that many coins to be spent or not. If the entry is not present in the current state, it will throw an error. If it is present, it will continue further. So the next check that will happen is it will determine whether the signature of the transaction is valid or not. So if it is not valid, it will throw an authorization error. And that could be the case in by mistake someone didn't sign it properly, or it could also be also be the case where the attacker has tried to spoof some owner, and they do not, however, own the private key. So there can be unauthorization error in that case. If we are passed through this error as well, it will now check whether we have the necessary amount of funds in the current state, which can be used to be spent in order to go to the next state. If we have that minimum balance requirement met, it will execute. Otherwise, it will throw an invalid transaction error. So this is how the entire flow looks like. And once we do not have any error, it will be successfully transitioning to the new state. And the new state will update now how many coins are left in the parent wallet. So with this new state transition, we can say that why not we just use this trivial mechanism in order to confirm the transaction. However, since it is a decentralized network, we want to ensure that there is some work done, and there is a mining and consensus algorithm correctly followed in order to append any transaction to the blockchain. So as we previously discussed the mining and consensus algorithms, after that state is transitioned, the transaction block is openly communicated in the network, and the miners now work on it. So once the miner is able to confirm the block successfully, and completed the mathematical challenge they are given, they will publish it to the network, and the network will verify their solution and append the block to the blockchain in case there is a 50 majority voting from the entire miners node. So once the update is populated in the parent chain, the other chains in the network will also append the newly mined block, and it will follow certain checks before appending. For example, based on the application of the nature, it could be possible that the block expires in certain time window. So it will ensure that that is not the case. It will check whether the proof of work nonce which is provided, is it valid or not for the block. If it is valid, and if the transaction is resulting in a valid state transition, then it will append to the other copies of the blockchain as well. So this step will be followed every time a mined mined block is being appended to the blockchain. So here, let's try to just understand the smart contract, how it is digitized using a programmable interface. So this is taking an example of Solidity code, where we are defining the very basic form of cryptocurrency, taking the definition here for coin. In this, you see there are different functions which could be called on this particular structure. We'll look at these two. For example, the mint function which is defined here. So you can see there is a condition which is being mentioned here. If the message sender is not a minter, then it returns. So what that means is the new coins can be created only by the contract owner. Otherwise, it will just not do any operation and return to the original caller. In case this condition is satisfied, the balance will be updated with the newly minted coin. However, the other function here, if you see, the send function can be called by any of the users in the network. So this will take in as input the receiver address and the amount that needs to be sent to the receiver address. Then again, it will check certain set of conditions, whether the balance amount, the current balance of the sender is less than the amount, then it will throw an error or return fail silently, basically. If there is enough amount, it will deduct that amount and add it to the receiver's wallet. So this is showing how a programmed smart contract look like, and what could be different conditions based on different use cases. And once those conditions are satisfied, the action is executed in case of the smart contract. So now that we have covered some of the basic components needed to understand blockchain, we can summarize it also to understand what are the drawbacks and what are the advantages. So definitely having blockchain, having the digitized form of smart contract and storing the data, it ensures end-to-end integrity of the transactions which are happening. It also improves the accuracy because there is no manual processing done in between. It is end-to-end automated. So it has higher accuracy as compared to the normal physical paperwork or the contracts we are doing. Then it eliminates any third-party verification, which helps in establishing trust and transparency. With the help of decentralization, again, it won't be everyone in the network will come to know if there is any tampering that is being done to the blockchain. So that is a good part. And as an application, it can be used for those countries or those places where the banking alternative is not very stable. So there it can be very useful. However, there are also few negative drawbacks for this blockchain. For example, it is difficult to trace any illegal activities. So that is one of the how we are getting the privacy, but that is also one of the major cons of blockchain. So it is difficult to trace in case of any adversary is able to steal the token, steal the coins. So that is one of the major drawbacks. Then it has also faced criticism from the regulatory bodies because of the unreliability on how it produces the coins and how it can be sustained. We also have data storage limitations. As the block continue growing with new transaction, it requires a lot of space to be stored, or even in case of the smart contracts which we are using to confirm the transactions, that can also be resulting in increased space usage. So yeah, others are slightly lower side. They are not very big drawbacks, but yeah, the transaction speed is slightly lower per second. And also we have the resources which are used in mining these new coins or mining these new transactions. That itself is huge because it requires finding cryptographic solution to some complex mathematical problems. So it ends up using a lot of resources as well. However, that's not a drawback in terms of security, but that is somewhere there is a room for improvement. So with this, we can see blockchain can be applied across multiple fields and different domains. Already we have discussed the cryptocurrency related platforms which are implementing blockchain technology like Ethereum, Solana, Bitcoin, and others. Then we have decentralized finance, which include like any loan, borrowing, or applying for any category of loans. So lending and borrowing business can be also considered under it. It will reduce a lot of paperwork and also ensure end-to-end integrity of the contracts. It is heavily used in NFTs, which is in the blockchain technology in gaming itself. So other important pieces, it can be used for legally binding the contracts, which are currently heavy paperwork again. So overall, it automates that like paperwork which is involved in the current scenario, and also offers end-to-end integrity and ways to audit it publicly. Then other similar things like there can be decentralized autonomous organizations, and e-voting system can also leverage this. E-voting system is an interesting use case for this, but let's see how we can, when it can use of this blockchain technology. So jumping to the attacks, the security consideration for blockchain. Now that we have covered a lot of aspects or the basics of blockchain, let's come to this interesting piece where we can just understand some of the basic attacks which can be executed in the blockchain network. So while we are talking about these attacks, we also want to understand what is the attack surface in case of a blockchain network. On a high level, if we try to categorize, the attack surface can be divided in these few categories. The blockchain structure itself. As we recall what we discussed in the beginning, there is a structure for the blockchain where it is stored in the form of a list, like a node pointing to another node in memory. So there, how the block header is maintained, how the block hashes are used for linking the chain together, and what are the other metadata that could be stored in the block header itself. So that comes under the blockchain structure. So there's a way where we can analyze if there are any security gaps in that structure itself. Then we have the blockchain network. Now the network is open to everyone. It is globally accessed across all the countries, and there are many users, there are many systems which are using it. So it has a very big scope of having the attack surface being discovered by any attacker, and there will be many attackers you'll be seeing in news, like who are trying to understand the public blockchain and trying to figure out any vulnerabilities. So since all the data is public, all the access is public, there is a high chance of any enumeration activities which can be done in order to exploit the blockchain network. We have the cryptographic algorithms which are being used in constructing either the new blocks or also ensuring that any transactions are signed. So cryptographic algorithms are heavily used in blockchain. So there are chances of also exploiting these algorithms. However, that is a very complex thing to crack, because most of the technologies are using the latest strong hashing algorithms. So it is difficult to crack, but we can also consider this under the attack surface. Then we have the implementation code itself, how the interface is designed, how the libraries are designed for that particular blockchain technology. And on the same lines, we have the smart contract. So there can be vulnerabilities related to code or the infrastructure being used. We'll discuss a few of these attacks in details in the upcoming slide. Won't be focusing on all the attacks, but yeah, we'll pick up few of the popular ones which were executed in the past. So here we have a list of different types of attacks which are possible in the blockchain network. They have varying probability of happening depending on the complexity of the attack needed and what is the discoverability of the attack surface itself. So first, let's just talk about compromising of multiple nodes in the network. Now that we know that any node, any user can join the network, so these nodes are not verified or audited by anyone. So there is no benign check done before they join the network. So there's a high possibility that attacker nodes are also joining in this network in order to figure out any vulnerabilities in the network and trying to exploit those. In this category, there had been few past attacks, which we will just go into details. So the first attack is the 51% attack itself. Here the majority, that is around 51% of the total network's hashing part is controlled by the attacker. This can cause forks in the blockchain. It can result in double spending or execute denial of service against some specific transactions and addresses. So what happens in case of 51% attack? As we have already discussed the mining and consensus algorithm, their majority of the network will vote to confirm that the new transaction should be appended to the blockchain or not. So since here the attacker is owning or controlling the 51% of network hashing part, they have entire control on any block they want to add to the blockchain. So they in that way they can just construct blocks with fraudulent transaction and append that to the blockchain, confirming based on their consensus, majority consensus. So here what they can do, for example, is they can append first a reversal of a transaction, and then they can spend the same coin, resulting in double spending. And also they can delay the confirmation of genuine transaction in the network. So when there are new transactions which are coming up, they will flood the network if they are not processed, mined in the right time. So this can lead to the denial of service attack, and any transaction which remains longer in the network, it will expire after a certain time. However, the 51% attack is it is not very probable on already established blockchain technologies. It has high probability of happening on the smaller businesses which are coming up, smaller projects which are coming up. So what we can do to mitigate the 51% attack is, if we can limit the maximum hashing rate which is assigned per miner or a group of miners. So that way we will limit the stake they have. We'll limit the consensus to also include other nodes in the network. And then there are other consensus algorithms also which can be leveraged in order to overcome this weakness. For example, proof of stake is one other algorithm which will result in more reliable response, and it won't be like biased to the attacker group. Here, in case of proof of stake, each of the miners who are interested in mining a particular unmined block, they will stake for certain amount of coins, and the one who has the most stake in mining will have higher odds of being given that mining opportunity. So the most affluent user is unlikely to perform such attack. That's why we can say it can be relied upon as much better as compared to the proof of work algorithm. Next, we also have related to the network attack, we also have Eclipse attack, which we can discuss. So in case of Eclipse attack, you will see it on the right hand side. We have a target node which is represented in blue, and we have the attacker nodes in red. So in this case, what happens is the attacker creates an artificial environment around one of the target nodes or user, which allows the attacker to manipulate that target node to do wrongful action or malicious transactions. So how they are able to isolate that target node? Let's just try to understand some very basic thing. So when executing this, the adversary attempts to redirect the target node inbound and outbound connection away from the actual legitimate participating nodes. So here on the diagram, you can see the white blocks are the genuine participating nodes. So the attacker nodes will try to redirect the target nodes inbound and outbound connection to only talk to the attacker nodes, and thereby it will isolate the target. It can result in illegitimate transaction confirmation because the target node is not communicating to any other genuine node, and it only has the data and consensus and mining data from the attacker nodes only. While these attacks are also rare, but they largely depend on the infrastructure of the blockchain itself. So a few mitigations which could be proposed for this Eclipse attack could be, if there is a way to randomly select the node with which the target node is communicating. So instead of just continuing to communicate with the attacker node, if they communicate any node in the network on a random basis, so that will reduce the chances of it being isolated with the attacker nodes. We can there can be an opposite method to mitigate as compared to random selection. That is a deterministic node selection. There we can hardcode in the particular target node to only limit the connections to some of the genuine nodes which are confirmed, and that way it won't be talking to the it won't be isolated by the attacker nodes. We can also increase the number of connections which are allowed for that target node, because most of the times why this happens is because there are like 8 or 10 outbound connections which are being allowed for the target node, and that's why it is limited in that attacker nodes network, where they can easily spin up less number of nodes. But if we increase the number of outbound connections allowed, the target node will now be talking to multiple nodes, so it can overcome that number and be able to talk to more nodes, not just limited to the attacker nodes. If there is if there is a way to also increase the difficulty for the nodes to join the network, the attacker won't be spinning up these malicious node at random. So that will also discourage any malign intent. However, that might impact other nodes in the network, so that won't be a very good recommended solution. So while these were the two major attacks which are related to any compromise of multiple nodes in the network. Let's talk about adversary in the middle. So adversary in the middle means, like, let's say there's a network communication which is happening, and there's a transfer of money from one wallet to another. In the middle, what can be done is the data can be tampered using mechanism like phishing, which we'll discuss in the upcoming slide. And there can be other methods. For example, if the system itself is compromised by some ransomware, there can be clipping attacks could be done, which will modify the destination wallet address, and it will transfer the money to the attacker's address. So that is a simple adversary in the middle attack, which can be done. Also, the data in the blockchain is propagating across multiple nodes. So there is a lack of censorship in that case. And there could be fingerprinting, which the attacker can try to leverage to trace any particular address and learn more information about them. Cryptojacking is one of the techniques where basically an attacker can compromise another user's resources in order to perform mining. So let's say you visit a website and they are able to deploy certain malware on your computer, and then they are using that malware to execute some of the crypto mining operations. So they are using up your resources and doing mining for themselves. Then dusting is also a small attack where the adversary try to send certain amount of certain amount of small transactions to different wallet addresses in order to gain as much as information corresponding to them as much possible. However, this in the current implementation, it doesn't have a bigger impact. Then the last but important piece is vulnerable smart contract. So as we go further in the slide, you will see many examples which are discussed for identifying vulnerability in the smart contract. Let's try to understand phishing. You might already be familiar with the concept of phishing, so but I'll just reiterate here. Here you can see there is a user who is trying to access Coinbase.com, but if you observe properly, the Coinbase has a wrong domain name, and it is trying to spoof the original Coinbase website. So the attacker can create such phishing pages which look very much alike the actual website, and it can fool the victim to access those and log in to those websites in order to steal their credential. And this can even bypass the multi-factor authentication you have. So here, when they go to this website, they will enter their login credential. And when the multiple factor authentication is being asked, they will also print in that token. And here you see the proxy is sitting in between. This proxy will redirect the request to the original server with the login credentials obtained from the user. So once we have that, the adversary is successfully able to log in to the genuine user session and being able to do any malicious action on their account, on their wallet. So in this case, since there is a bypass of the MFA itself, so what could be the mitigations? Let's just take a quick look. So since the URL being accessed here is a phishing URL, we should always be wary about what URLs we are accessing. So ensure that you do not go to any similar looking URL. So be very careful about that. Then apart from that, the TLS checking can help here because this proxy won't have the same TLS certificate as the original Coinbase website. So if there is a way to, like if the user can pin the TLS certificate, original TLS certificate for Coinbase.com on their device, that will prevent them to go to this website. Then we have dynamic linking, which is also called creating a dynamic key, which is based on double confirmation actions. So when we first log in via MFA, let's say there is a transaction being performed, and any adversary in the middle, they are able to modify that transaction and send it to the server for processing. So the user will get another notification on their device. Let's say they are using a mobile phone for confirming on the second part of the transaction. So the server will send another notification to the user to confirm that they have made a transaction of this much amount. So if the user is they agree with the transaction, they will confirm it with their biometric, let's say fingerprint, and there will be a random key generated that will encrypt the data and send it back to the server. So here this can be used to mitigate even if the adversary is able to modify the transaction in between. Then other ways could be detecting anomalies in the user sessions activities itself. So this we cover the phishing aspect. Then in case of smart contract, there are multiple vulnerabilities which should be taken care when we are developing one. So unhandled exception, even though they can look a very small issue, they can be looked upon as a bug, but they can lead to inconsistent state in the wallet or the blockchain, which can be exploited by attacker in case certain conditions are met. So here, if you see, there is a contract which is defined, and here there is a function called withdraw. Withdraw function allows a certain amount to be withdrawn from the wallet. So when this function is called message.sender.send. There is no exception handling on top of this function. So it is a possibility that this function can silently fail. In that case, it won't throw an error, but the amount will be deducted from the sender wallet. So this can, if this keeps on happening, this can result in negative balance as well, leading to inconsistent state in the blockchain. So this might look a small error, but these should be avoided, and there should be a proper exception handling done in the smart contract. Then let's talk about external calls. So external calls, this is a very important piece which we should take care when we are reviewing the smart contract code. Smart contracts alone cannot get information about real world events because they cannot send direct HTTP requests by design. So they rely on some external information that could be that could jeopardize the consensus. In case of cross-chain addresses, for example, when we are using any address in one particular contract, the same address could have a different entity in the other chain. So the address is not unique across the chain. So that also should be kept in mind before, let's say, giving any permission to a particular function and assigning that permission to a wallet at a particular address in the other blockchain. So this has to be kept in mind that the cross-chain addresses could be very different. So ensure that the address you want to use in case of cross-chain use cases is correctly verified. We should also avoid changing states directly after the external call. What that means is, since the external calls are unchecked, they are not very trusted and can execute some malicious code. So we cannot anytime trust those. So there should be row-level checks which need to be implemented on the on your contract side, and instead of relying on the external calls. So let's say if there's a call being made to external contract, then whenever it returns, ensure that the current state after that call is valid by doing certain validation. For example, what is the current state of the state variables, whether the state variables are within the limits or they have the necessary validation still successful. So these kind of checks should be done before just after the external calls are made. And once these checks confirm that they are valid, then only change the state. Okay. There is another aspect where we should favor pull calls over the push calls. So that means, like, whenever there is a necessity to call any function in external contract, you should call it from the original contract instead of having a callback from the external one. We should be isolating these external calls as well, so that they do not impact any other functionality in the blockchain. So what could happen is, let's say there are two functionalities which are calling different external calls, and one is like simultaneously called. It can result in race condition. So try to isolate these external calls so that they can do their action independently. Next, we have the delegate call. So this is one interesting piece, and it has been one of the it is called the dangerous call. So this shouldn't be called in case of smart contract, and it should be avoided as much as possible, and especially for the contracts which you cannot trust. So in case of delegate call, the contract works in the same context as the caller contract. So they have the same storage variable values. So the context remains the same. So if the caller contract is calling the target contract, they will be able to modify the value which is used in the target contract. So let's take an example here. This will help you understand better about the delegate call attack. So we have a contract called lib here. Inside lib, we are having a function called pwn con. Then we have another contract which is hackme. So this the hackme contract can be considered as the vulnerable contract. This has the state variable owner and the reference to the lib contract. So it takes, when we are constructing the hackme contract itself, it takes into account the lib address, and the owner is assigned the value as whoever is the caller. So the sender of caller is assigned as the owner of as the owner in this variable. Then we have the lib also initialized here as the reference of the library function. Here there is a fallback function which is defined. So fallback functions are called when there is either there is some error in calling the function, or when there is a non-existent function being called from another smart contract. So this will be the fallback function. So let's say we have the aim to modify the owner of this hackme contract using delegate call. So let's try to see how that can happen. If we modify the owner, then basically the current owner will no longer be able to update this contract or do the critical operations in this contract. So for that purpose, we build that adversary can build another contract. On the right hand side, you will see this is called contract attack, and here it is taking in its constructor the address reference for hackme, which is this contract, and then it is calling the hackme contracts function, and this you can see pwn function it is calling. However, there is no function called pwn in case of this hackme contract. So this since there is no function existing with this name, the flow will go to the fallback function which is defined here. And inside this fallback function, you see that the library function, library contracts function is called, and the input which is being sent is the caller message data. So in this way, like the caller message data here was pwn. So now what it will do is it will delegate the call, and pwn will be sent to be called using the lib contract reference. So basically this function they will be able to invoke, even though it was not exposed from the lib contract directly. So now that we are able to at least modify the flow for the hackme contract, and the attacker is able to reach the pwn function here, this function will be used to assign the ownership to the attack caller itself. So as we discussed that in case of delegate call, the contract work in the same the target contract work in the same context as the caller contract. So basically now the owner will be assigned the attacker's address, and eventually you will see that the data here for lib and the hackme is modified to the attacker address. So here we are able to hijack the hackme contract and own it, shift the ownership from the original owner to the attacker address. So that's why delegate calls are dangerous, and we should try to avoid it in the smart contract. Only for cases where we are fully sure that there is no issue and it has been securely developed, it can be leveraged. Next, we have the integer overflow or underflow. So arithmetic overflow underflow can happen in any of the languages. For example, in C also you would have seen that any variable which is having let's say maximum size of 32 bits that can overflow in case a number greater than the acceptable limit is assigned to it. So here if you see, we have a uint 256 value which is being defined, and also the balance is also defined as uint 256 data type. So it is unsigned integer 250 of 256 bits. So if we reach the maximum unsigned integer value, that is 2 raised to power 256, it will circle back to 0. So since it is now circling back to 0, here it can lead to inconsistent state. So these are the considerations which we should take into picture. And it's not only about the balance parameter right now, but there can also be certain cases where there is a condition which is being which needs to be satisfied based on the input value, and if that condition is of let's say type unsigned int, it can be overflown by having a data beyond a certain limit, and that can result in the bypass of that condition. So look for these kind of errors. These can lead to security issues. Then we have another important attack called re-entrancy attack. Here, the adversary can take over the control flow. The simplest version of this technique, it involves the function that could be repeatedly called before the invocation of the first function is completed. So here you can see there is a contract A, which is defining these functions: check balance, send fund, and update balance. And contract B has a fallback function which keeps on calling contract A for updating the balance and sending the funds. So the contract B can be malicious, and it can recursively call the sending funds function, which can result in draining of the funds from contract A. So this is the simplest form where we can drain the funds using recursive mechanism. This will give you a clear picture in the code itself. As you see here, there's a function called withdraw, and the balance is first calculated. If the balance is greater than 0, it will call the sender function. It will call and perform the withdraw action. So the attacker contract, what they can do is, as you see here, there is a fallback function which is defined, and this will call deposit funds contract, which is on the left side. It will call the withdraw function for that. And this is another function attack, which will initiate the call to the withdraw function. So before the this first withdrawal itself is completed, and the state updated balance is reflected in the original contract, it will keep on calling the recursive function using this fallback withdraw function being called, and it will keep on draining the funds there. So to prevent this, there should be a check, there should be an update in the state prior to making the call. So if we are sending a certain amount, if we are transferring certain amount, then the balance should be updated prior to actually executing the send command. Or if the balance is withdrawn from the wallet, then it should be set to 0, so that any new recursive function calls will be prevented, and it won't be able to drain the funds or lead to an inconsistent state in blockchain. Next, so re-entrancy attack, the simplest form we just discussed. Then there can be also re-entrancy attack in multiple functions, that is called cross-function re-entrancy. So here if you see, we have two functions defined. One is transfer function and one is withdraw balance. So let's say the withdraw balance is called, and it will try to update the balance to 0 once the withdraw amount is successful. However, the adversary can call the transfer function also in between before the state change is reflected. So they will be able to transfer the fund even though there was a withdrawal being initiated in that particular contract. So this is called cross-function reentrancy, and it can also be implemented in similar way as we discussed, where we can update the state to reflect the new balance that can prevent any recursive call to change the state of that particular wallet. Then we have the public visibility aspect of blockchain. Now that blockchain is public in most of the scenarios, the attacker is able to do full enumeration on the network. They can audit the transaction, they can read the implementation code, the smart contract, everything they can access publicly. And with this, they are able to figure out any gaps in the implementation or any information which can be useful for triggering an attack. So on a high level, the flow will look like this. The attacker will search for vulnerabilities in the smart contract. Then they, based on zero knowledge, they will try to perform different actions and perform different actions. If they are able to come up with able to identify a vulnerability in the network, they will perform an attack and can either demand a ransom or report the vulnerability, anything that can be proved. So this overall covers multiple attacks which are pretty common in the current development of smart contract. Then denial of service can also be caused based on different flow which can be included in the smart contract. So that can result in denial of service, or there can be hard-coded variables also in the implementation itself, which can be leveraged to compromise either the blockchain structure itself or the smart contracts. Then, let's just take a quick look at few of the popular blockchain attacks. So in the past, there had been a 51% attack, which was in 2018, where Bitcoin gold was affected. So we already discussed the 51% attack, where majority of the total network was controlled by the attacker. Then there was also the DAO attack, which is decentralized autonomous organization attack. It was executed based on exploiting the reentrancy vulnerability, which we just discussed, and resulted in draining of funds from the target contract. Then, the other one is wormhole attack, which was in Solana. This was a vulnerability which was exploited in a software component, which is a dependency of Rust library, where there was a gap in verification of the signature. So we won't be going in much detail, but on a high level, the idea is that there can be vulnerable components which could be imported in the implementation libraries. So ensure that there is a correct dependency security review before using it in the implementation of the platform. So I guess, we are done with the discussion here. Let me see if there are any questions I can take.
I don't see any questions actually. So maybe I can ask a question.
Yeah, sure.
So you mentioned about the calls which we get from, or we do it in the smart contract, like accessing the external libraries, right? So do you mean by not just libraries, but SDKs also, like a whole SDK could also be possible to be accessed from the smart contract, and the vulnerabilities could come along with it?
So there are two aspects. One is the one we discussed here for external calls. That was primarily focused on calling external calls in separate contracts.
Yeah.
So this was focused on the smart contract, cross smart contract calls. But yeah, there are the attack which we just saw, which was wormhole bridge attack on Solana. That is related to exploit using a vulnerable library which was used in the implementation.
Okay.
Yeah.
Okay, so it's possible to use, because I think this feature is not available to all of the smart contract languages, I could say. I think only Ethereum has it. I mean, I'm not sure about all the smart contracts, but with Solidity and Ethereum smart contract, you can have it. And I guess there comes security vulnerability. If you
Yeah, it will vary based on different blockchain technology, right?
Yeah. So I see two questions. Okay, so Komal asked, thank you for your rich talk. May I have some explanations about dusting? Slide 12.
Yeah, so in case of dusting, it is not a very high impact attack, I will say, as of now, because already the information, there is a good amount of privacy maintained in the blockchain. So what dusting exactly does is it will be sending certain amount of balances to multiple wallet addresses in order to see what are the data it is getting in response. And based on that data, it will try to collect information collect the information in order to see if they can de-anonymize or unmask those destination wallets. So they are just trying to collect that information, but given the privacy of the blockchain, at least the current established technologies which are using on this platform, there you won't be able to see much information. But that is the technique the attackers try to leverage in order to unmask or de-anonymize the destination addresses.
Yeah, thank you. I hope, Komal, you got the answer. So does anyone have any questions? Okay, yeah, you're welcome, Komal. Yeah. So
yeah, I hope this was not something like everyone is able to understand, and please shoot any questions you have, because this will help in also in the future talks we can have in this vertical.
yeah, definitely. I mean, yeah. So someone raised hand. Okay. Josmari. Okay. Yeah, go ahead.
Hi, I was wondering if there is any part in the resource where I can find any queries that will help me with to prevent these vulnerabilities that you have present when creating a contract. I see there is a lot of courses in there, but I am wondering if there is a specific one that can help me with this.
Sure, I can. Like there are multiple tools which can be used for auditing and checking the vulnerabilities. I can definitely share some links after this session when I Manjiri, we can share this content as well, right?
Yes, yeah. The talk will be posted. Yeah.
Yeah, so we can send it out on the email. Any references in that regard.
Yeah, we can do that. Okay, so any other question? She asks, can we have a look to the references? Last slide.
Yeah.
Do you have any question based on it, Komal?
Yeah, so Ethereum documentation is a super good place for understanding this. entire concept. They have also listed multiple security aspects. So definitely, it is a good point to start with if you are a beginner.
Yeah, we will share the slides, and so basically this recording will be posted in next week. So yeah, please join the Slack channel so you could find the YouTube link. So let's wrap up. Yeah.
Okay.
Thank you, Swati, for such a wonderful and insightful session. The topic was quite intriguing and make me explore it more. So
Thank you so much.
with code samples, you made it so easy to grasp. Yeah. So
Yeah,
really
actually, just before that, like I know the overview we were giving there, we didn't have much hands-on, but through the codes, I thought like that will give a better picture to understand our issues.
Yeah, definitely. I really hope all of you got gist of the importance of security in blockchain, and even specifically in developing the smart contract. So thank you everyone for joining today's session, and please note that we will be posting the recording in few weeks, and we will add the link in the Slack.
Thank you so much, everyone. Bye.
Thank you, everyone. I wish you all a pleasant evening. Bye.
Bye.